we can get started with the second talk. So this is a paper, this is one of the distinguished papers at ICFP this year, and it's a functional Perl as well. And Gan's going to give a presentation. Please start.
Okay, thanks for the introduction and thanks for attending my talk. Hello everyone, I'm Shen. I'm a third-year PhD student from University of California, Santa Cruz. Today I'm going to talk about HasChor, functional choreographic programming for all, which is a functional POR. And this is a joint work with Shun, Kashiwa, and Lindsey Kuper. To begin with, I want to talk a little bit about what programming distributed system is like. So distributed system consists of a collection of nodes operating independently and communicating through message passing following a protocol. Traditionally, to implement such a system, developers write individual programs for each node and hoping their joint execution would give rise to the correct behavior prescribed by the protocol. As a simple example, let's say if we want to write a client-server protocol, obviously there are going to be two nodes, a client and a server. For the client program, we might write something like send a request to the server and wait until receive a response back from the server. For the server, we might write something like receive a client from the client, process it, and generate a response, and send it back to the client. As this example shows, these individual programs use send and receive to communicate messages, and it is crucial to ensure the send and receive matches with each other. Otherwise, we will get communication errors. A typical example of communication error is a deadlock. For instance, in the client-server protocol, if both client and server are trying to send a message to the other, then neither will make progress and the system will deadlock. Although this is a simple and contrived example, and I'm sure most developers can spot and debug this deadlock very easily, but imagine you're building a complex protocol where there's tons of communications going on. Having to pinpoint and debug a deadlock like this can be very painful. It would be great to have some language support that prevent us from writing programs with communication errors. To that end, several techniques have been proposed, and choreographic programming is one of them. The key idea of choreographic programming is that instead of writing individual programs for each node, developers write a single program that describes the complete behavior of an entire distributed system. We call such a program a choreography because it coordinates nodes in a distributed system just like a choreography coordinates dancers' move. In a choreography, send and receive are combined into one operator, and this operator guarantees that send and receive are always matched up, thus there's no deadlock. Additionally, choreographic programming provides a compilation process called endpoint projection to generate individual programs to be deployed on each individual node. So with the choreographic approach, the client-server protocol can be implemented as a single program. In this choreography, we describe both the client and server's behavior, which makes the protocol manifest. Another benefit of choreographic programming. A central piece of choreographic programming is this squiggly arrow operator, which we call communicate, or shortened as COM, as it represents communication between two locations. Here, on the first line, the client is communicating a request to the server, and when the server receives that request, it binds that to a variable X, and the program continues. After writing this choreography, if we want to get executable code to be deployed on client and server, we use the endpoint projection, which will generate these two individual programs that are exactly the same as the hand-wrote one we saw before. So that's choreographic programming, and we believe it's an interesting idea and want to bring it to the functional programming world. As a result, in this paper, we built HasChor which is an embedded domain-specific language for choreographic programming in Haskell. Haskell provides a monadic interface for choreographic programming, where choreographies are expressed as computations in a monad. As an embedded DSL, unlike previous implementations, HasChor doesn't require a customized compiler, so it integrates well with existing Haskell ecosystem. And also, our embedding makes heavy use of Fourier monads, which leads to a very natural realization of endpoint projection, which I will show in a moment. So now I'd like to give a tour of HasChor and show what choreographic programming looks like in it. Let's consider a standard protocol from the literature, the bookseller protocol. In this protocol, the buyer is trying to buy a book from the seller, and the protocol begins by the buyer sending the title of the book they want to buy to the seller, and the seller replies with its price, and the buyer decides whether or not to buy the book. If it decides to buy the book, then the seller sends back the delivery date of that book. Otherwise, the protocol just ends there. In HasChor, a choreography is represented as a monad that returns some value. Here, the choreo monad is the monad for choreographies. And the bookseller choreography returns a value maybe day at buyer. So in HasChor, values of form A at L are called located values. Intuitively, A at L means a value of type A at location L. Why we need located values? Because in choreographic programming, we have a global view of the system. So values at different locations will show up in the same program, which makes it possible for location to access a value that doesn't reside on it. So to prevent such behavior, HasChor annotates each value with its location, and we make this located value opaque and not immediately usable. To use it, you need to unwrap it by applying an unwrap function, and HasChor provide this unwrap function in a very regimented way, which I will show in a moment. Additionally, this choreo monad is also parameterized by another monad, which represents the kind of local computation that each node can do. For realistic programs, most of the time, this monad will be I/O or variants of it. Now we are ready to implement the bookseller protocol. As the protocol prescribes, the buyer first sends the title they want to buy to the seller. In Haskell, we use this locally operator to perform a local computation. So here, the buyer is doing is querying the standard input to get the title of the book they want to buy. This locally operator takes the location L and the action MA and returns a located value at that location in the choreo monad. And notice this local action MA, it has access to an unwrap function that can only unwrap located value at that location. This is the only place where Haskell provides this unwrap function. And note how this L is matched up with the location who's performing this computation. This is how Haskell guarantees safe access to located values. In this example, the buyer actually doesn't use the unwrap function, but you will see it gets used in later example. Moving on, once the buyer has the title they want to buy, they need to communicate it to the seller. And in Haskell, we do this by using the communicate operator. So the communicate operator takes a pair of a sender location and the value at that location and the receiver location, and then returns a value at the receiver's location in the choreo monad. In this example, title is a string at the buyer location, but after we apply the communicate operator, title prime will be a string at the receiver's location. Going back to the bookseller protocol, after receiving the title, the seller now needs to send the price of the book back to the buyer. And we do this by writing these 2 lines of code, and pretty similarly as before, here seller is doing another local computation to get the price of the book. Here we do need to apply this unwrap function to title prime to unwrap it and use the normal function price of. And once the seller gets the price of the book, now it communicates it to the buyer. Moving on, at this stage of the protocol, now the buyer needs to make a choice, and this choice will change the follow-up choreography. In HasChor, well, first we need the buyer used locally to make this decision, basically checking whether the price is within its budget. Now it needs to make a choice. In HasChor, we use this count operator to express conditionals. So this count operator takes a pair of a location who's making a choice and the choice value at that location, and the function that describes the follow-up choreographies based on this choice. And the operator returns one of the follow-up choreographies. Here we count on the decision at buyer. If it's true, then the seller will send a delivery date of that book back to the buyer, and the buyer return that date as the result of the whole choreography. Otherwise, the buyer just return nothing as the result of the whole choreography. Zooming out, this is what the complete choreography looks like. Now let's switch gears to talk about Haskell internals, and in particular, how endpoint projection is implemented. So as we saw before, the programming model of Haskell is structured around this choreo monad, which has these 3 effects or operators, locally for doing a local computation, com for communicating a message between locations, and con for conditionals. On the other hand, each node needs to run individual programs, and we call these programs network programs, and they're expressed as the network monad in HasChor. And the network monad has these 4 effects. Obviously, it needs to be able to send and receive messages. It also needs to be able to broadcast a message, because when we implement the con, the location who's making that choice needs to broadcast the choice so the other nodes can know which branch to take afterwards. And also, network program needs to be able to run local computation. Now we can think of endpoint projection as the process that links up these 2 kinds of programs. In HasChor, endpoint projection is defined as a function that takes a choreo monad, a location, a target location, the location we're projecting to, and generates a network program that implements that location's part of the choreography. And like we discussed before, the choreo and the network monads are nothing more than computations with these 7 effects. So in a sense, we can think of endpoint projection as interpreting the 3 effects in the choreo monad in terms of the 4 effects in the network monad based on the target location. For example, if for the locally effect in choreo, if the target location is location who's performing the local computation, then we interpret it as a run. Otherwise, it's a non-op. For com, if the target location is the sender, then we interpret it as a send. If the target location is the receiver, then we interpret it as a receive. Otherwise, it's non-op. Conditionals are slightly more complicated. As I said before, in choreographic programming, when a node makes a decision, such as taking one or another branch of a conditional, other nodes need to be notified. So we interpret this as a broadcast. For the node who's not making a choice, we interpret it as a receive, and then recursively interpret the follow-up choreography. Now that we have the basic idea of endpoint projection, to actually implement it, there's one more question, which is how do we interpret effects in a monad? And the answer to this question is Fourier monads. Fourier monads were originally proposed by Oleg, Kashiwa, and Hiromi Ishii in their 2015 Haskell Symposium paper about building extensible effects. The key idea of Fourier monads is a term representation of an effect for computation, which leads to the following definition of Fourier monads. So a Fourier monad is parameterized by an effect signature F that specifies the allowed effects in the monad, and its two constructors, return and do, corresponds to the two operators of monads. And note how this Fourier monad is defined as an algebraic data type, which means we can manipulate them just like normal data types, which allows us to write an interpret function that interprets the effects in a Fourier monad in terms of operation in another monad. So here, the interpret Fourier function takes an effect handler that maps effects in F to monadic actions in G, and the function basically just folds this effect handler over the Fourier monad. For the return case, it's pretty simple. We just return the same computation in G. For the do case, we call the effect handler on the effect and then bind the result to the continuation to get the follow-up computation and recursively call interpret Fourier on the follow-up computation. And the Creel and the network monads are defined as instance of the Fourier monads. So here, Creel is defined as Fourier monads instantiated with Creel-seq effect signature, and network is defined similarly. And with all this definition, now we are finally able to define our endpoint projection as interpreting effects. And I want to draw your attention to these two lines here. So essentially, this endpoint projection function is a call to interpret Fourier with a handler that translates the effects in the Creel-seq effect signature into actions in the network monad. So now we have the basic idea of Haskell's Fourier monads-based implementation, but there's more in the paper. And in particular, like I said, the network monad is also defined as an instance of Fourier monad, and we use the same functionality provided by Fourier monad to support swappable message transport backends. For example, Haskell provides a HTTP backend where we interpret send and receive as sending and receiving of HTTP packets. There's also a local backend where we interpret network monads as threads and send and receive as writing and reading envars. Second, so the types of the operators I showed you in this slide actually use dependent types. And as we all know, Haskell is not a fully dependently typed language. So in the paper, to actually implement these, we have to use some type shenanigans to approximate dependent types. And Haskell also support advanced choreographic programming features like higher order choreographies and location polymorphism. The nice thing about this is that we didn't actually spend too much effort on implementing this because we embed this in Haskell. And Haskell is itself a higher ordered and a polymorphic language. So we actually get these features for free. And lastly, there's also a case study on implementing a replicated in-memory key value store in HasChor. So to conclude, we present HasChor, the first embedded domain-specific language for choreographic programming, and we show Fourier monads can be used to implement endpoint projection in a very natural way. And there's one more thing. A week ago, we received an email from a user outside of our group who's trying to use HasChor to implement an rsync clone. And he complimented Haskell for being very accessible to use. The nice thing is you don't need to understand any details about Fourier monads. The surface interface is very easy to understand and use. And we believe that really shows Haskell sort of help advance the practicability of choreographic programming. So if you are interested and want to try out HasChor, it's available at this GitHub repo. Thank you.
So one possible motivation for writing distributed programs is to take advantage of parallelism. But the programs you've shown us so far are all sequential. Is there a story on parallelism? And if so, what is it?
Can we use choreographic programming for parallel programming? Yeah. I would say right now our focus is about concurrency. So I think eventually in the future you can use it for parallel programming. But right now, yeah, we are focusing on having concurrent entities. Yeah.
Simon, introduce yourself.
Hi, lovely talk. Simon Fowler, University of Glasgow. I was just wondering about your endpoint projections. So you had the lock data type, but I didn't see that constrained anywhere. I was just wondering whether you could statically guard against providing a location that wasn't actually in the choreography.
That's a good question. Well, so the question is, how do we represent this location? And what if we project a choreography to a location that doesn't show up in the choreography?
Yeah.
The answer to that is, if we project a choreography to a location that doesn't show up in the choreography, we will get an empty local program that does nothing. It's still well defined that endpoint projection is a total function. It's defined for all location. But if you project it to a location that doesn't show up, it would just do nothing because the choreography doesn't say the location should do anything.
All right, so I'm Alan Jeffrey from Roblox. Okay, so the short version of my question is monad versus applicative functor. The slightly longer version of that is that the difference between those two is whether you can do ahead of time endpoint projection or whether you need to do endpoint projection during the running of the program. So I was wondering if you had use cases where you actually need the ability to do dynamic endpoint projection.
Okay, so there's two questions. First, monad versus applicative functor. I suppose you're asking, can we implement this using applicative functor? I would say the answer is yes and no, because you see we have this conditional in choreographic programming, and with applicative functor, you cannot, so the control flow is fixed. You cannot alter the follow-up computation based on the result of a prior computation. But recently, there's this work on selective applicative functor, which add a combinator represent conditional in the applicative functor. So we believe maybe using that, we can model choreographic programming. And the second question is dynamic versus static. I think right now what we are defining here, our endpoint projection is a dynamic function. So when you run your program, that's the time when endpoint projection actually happens. Do we have a use case for this? Right now, no. But yeah, I don't know, maybe there will be some in the future.
Arno Spivak, Twig. Yeah, the whole safety thing for location is quite clever, the unwrap thing.
but it's a lot of boilerplate, right? So it bothers me a little. So I have a very stupid idea, and you stop me when it's too stupid, okay? So you introduce a type class at location, and now x at L becomes at location, fat arrow, x. Then locally, instead of introducing a function that lets you unbox a type, just give you an at L instance locally. Would that work? Or something?
You're proposing a solution.
No, well, yes and no, because I'm not sure it's correct. So
First, I want to say I agree with you that having to use this unwrap function in the current monad is a little painful, and I want to address that issue. But I don't quite fully understand your proposal. Maybe we can think up later after this talk. But I'm curious to know.
Carter Schoenwald, TBD. So I'm wondering, do all these properties work out even if the protocol is recursive?
Even for protocol?
Because the projection for a missing counterparty, depending on how the recursion is written, seems like it could get stuck.
So the question is, does the endpoint projection works for
a recursive protocol?
It does, actually. So I mentioned that in the paper, we have a case study on replicated key value store. And that key value store is basically in a service loop where you take some request, process it, and send it back, and then recursively go back to take more requests. So, and the EPP function works well for that. So I think, yeah, we can handle recursive protocol like this.
I'll ask a question from Discord. Edward Torok, apologize if I mispronounced that, from Zen server. Freer monads are great, but would it be possible to also use Freer applicatives for running locally? For example, to support Haskell, like to do batching, etc.
I think that question is very similar to the question, sorry, I forgot, Jeff asked. Yeah, the short answer to this is yeah, but you need selective applicative functor, free selective applicative functor to say it. Well,
this all looks. Am I close enough? Yeah, I need to eat the ice cream. This is all. It looks really nice, and your experience all seems to be mostly positive. You mentioned a few little quirks here and there, but normally when we do these kinds of embeddings in Haskell, there are some pain points in practice, and I'm wondering what are they here, and in order to make this, well, if there are such pain points, would you want some additional features in Haskell, or would you want to do this as a standalone language elsewhere? I know there are existing choreographic programming languages. Have you learned something here that you could transfer into one of these existing?
So the question is, are there any inconvenience in embedding these in choreography programming in Haskell? Yeah. I think there's some pain points like the proposal that guy just proposed. So having to use this unwrap function to make sure safe access to located values is a little bit cumbersome. And if we were going to make our own language, I think we can have a customized typing rule. So every time you access a variable, that's actually is of type. That at another location there will be a type error, so you don't need to call this unwrap function every time.
Well, that seems relatively minor. I mean, are there bigger issues?
To say some other pain points.
You've got 25 seconds to just run the clock down.
Well, I would say our experience with embedding this in Haskell is Haskell is relatively smooth. Yeah. other than
Well
this.
done.
Let's wrap it up there. Thanks for answering all these questions.